lot of I can statements. This is our last lesson of the unit. Test is coming up this week on Friday. You'll notice if you look at the work week up here and the work, what we're doing. So today, page 470 from the textbook. Tomorrow we're doing the worksheet F7. Then we're going to review what's on the test on Wednesday, another textbook assignment. And then we are doing Pearson quizzes on Thursday in class, answering some questions. And by the time you take those tests, those Pearson quizzes need to be done. So I've already put them up, but I would like you to kind of wait for class on Thursday to at least do some of them, even if you're working ahead. So as we are taking a look right now at the I can statement. So I can define a geometric sequence. So we're going to think about what is our sequence. I can tell if it's linear or exponential. We've already been working with that. Same thing in a sequence. So when we were looking at our tables trying to decide linear or exponential, we looked for constant addition, and exponential our tables were constant multiplication. Same thing with our sequences. So distinguishing between geometric, that's the multiplication, and arithmetic, which is your addition. Writing both explicit and recursive again for the geometric model. Being able to generate more terms in our geometric. I can explain that a recursive formula tells me how a sequence starts. So when I look at the recursive, it tells me the start point and what's doing to the previous one to generate. And then in an explicit formula, it tells me the elements of the sequence, knowing the previous one, and then going between the two. So if we think about our sequences, what could you tell me is a sequence if we are thinking about that? Chase, what do you think for a sequence? It's like a list of what?
A list of numbers.
Yeah, and they're usually related to each other, right? So when we did them earlier this year, that list of numbers, we might have had something like 1, and then maybe we have 3, and we have 5, and we have 7, and that was an arithmetic sequence, right? We now are going to be looking at, so the types that we learned earlier this year, those were our arithmetic. The arithmetic is when you have a common difference, remember? And when you were looking at that common difference, when we did our arithmetic, you were either adding, like in this case above, adding 2, or you might have been adding like a negative 2. So you're either adding or you were adding a negative to get that next number in your term. It didn't matter what you were looking at, but you were looking at a common difference. And that common difference in our linear equations is really our slope. So point slope form, if we think back to our arithmetic equations, they were kind of like point slope form as we looked at those. So just a little review on the bottom of that next page, or that next same page. Arithmetic sequence is when you add a constant amount to each term. So the recursive formula, we had this on our final, right? A to the 1 equaled a to the n. To a to the n minus 1, telling us this is just our previous term. That's all that means, is previous. When I see that n minus 1 plus my common difference. And that common difference, when we were looking at it, that was really our slope or our rate of change. The explicit said we could choose either one depending on it. A lot of times, this is the one that most of you chose, a to the n, equaled that common difference slope. A lot of you went with n minus and like 1 plus, and then you told me what the first term was. How did we get n minus 1? Because when we looked at the recursive formula, we could see over here. So it says if we're going to practice writing a recursive formula for this sequence. So what would we say our beginning term is, our a to the 1, if we are looking at this? So tell your shoulder partner, and we're going to start writing this. So our recursive formula should be a to the 1. If I'm looking at it, what would you say, Erica? A equals 2. And if we are looking at what's happening in this one, it looks like we are continually doing what, Cal? Decreasing by 4. So this is going to be definitely arithmetic, right? So we're going to start with a to the n. A to the n minus 1, that's our previous, and then a minus 4 for n minus 1. Making sure that this is like a subscript. So now we want to do our explicit formula. And the easiest part from our explicit formula is to go with a to the n. and to go with our first term. So first thing we know it was a minus 4. So we might go with, if we are thinking about this, our common difference, which is going to be a negative 4. And then we're going to have n minus 1, yn minus 1, because we can see 1 here, and then plus 2. If you don't like it written this way and you want to distribute this out, you could do that, but we're not looking at having x's in this one. If you would use a distributive property, you would have had a to the n is equal to negative 4n. This would have been a plus 4 plus 2, and we would have had plus 6. So if you would have had the 0 term here, the 0 term would be 6, because you had to add, if we are looking at that one, a negative 4 each time. So going back, this would have been, if I'm thinking about it, the 0 term, right? How else do we think of the 0 term? We think of it as our y-intercept as we look at that, okay? So as we are looking at this, that's kind of our first part, just a little bit of refresher. So now we're going to look at geometric on the top of the next page. So when you look at page 24, it says a geometric or exponential sequences are sequences where you multiply each term by a constant ratio or a constant multiplier to get the next one. So it looks the same, g to the 1. Then you are looking at r, which is your common ratio. This is what you are multiplying by, right? Whatever you're multiplying by. Someone said, well, what if you're dividing by 2? Well, dividing by 2 is the same as multiplying by a half. Dividing by 3 is the same as multiplying by a third, right? So we want to use it as multiplication, not division. Explicit formula looks very similar. G to the n, our term, but r, but instead of having it as like a parenthesis n minus, we're going to put that up here, and we are going to be putting the term in this way. So if we are looking at writing this recursive formula for the first one, if I am starting out, I'm going to start with g to the 1. As I am looking at that, g to the 1 would be 3. What does it look like I'm taking 3 times to get 15? And my hint is always divide the second by the first. So if I take 15 and I divide it by 3, that gives me 5. This is trying to tell me my constant ratio. And if I do the same by taking 75 and divide it by 15, I'm still going to get 5. 375 divided by 75, I should always get that same ratio. So if I am looking at my recursive formula to start out, my recursive formula, hopefully you have something like this. G to the 1, 5, times g to the n minus 1, and we always want to finish with that n greater than 1. So when I start here, if I am looking at the first term was 3. So I'm going to put g to the n equals 3 as I'm looking at this, to r to the n minus 1. That'd be one of my formulas I could look at, right? So I just want you to be aware that there are many that I would count correct on this part, right? So when I am looking at this, there are many that could be correct, because if I look at the h value, if I go n minus 1, I'm going to use 3. I would take it correct if you wanted to go with the second one, 15, and then it's going to be n minus 2. We wanted to go to the 0 term. I'm not sure why you would, but most people would go with the 75, and I'll tell you, most of you would probably use this one. This is just the easiest one if you know from the recursive formula. Those are already there. But if you think of before this, if you had to take it times 5 to get 3, you had to have 3/5, and it would have been r minus 0. So if you want, this is the fifth term of a geometric sequence is 140, and it's a multiplier of 2. So if we are using that information, what we know is that g to the 5 is actually equal to 140. And they are asking us to find the 6th term. So this is our given information. So what we know is to find g to the 6th, we should be taking the previous term, so 140 times 2, right? So we get 280. But now they ask us to find the first term. So we could go backwards, right? So g to the 4th, we take 140 and divide it by 2. G to the 4th should be 70. How do we get it? Because we're going backwards, times 2, right? G to the third should be, half of 70 is 35, right? G to the second, we're taking 35 and we're dividing it by 2 to get 17.5. So our G to the 1 in this sequence started off at 17.5 divided by 2 gives us 8.75. So if we are looking at that term, and again, we're just going back and using that repeated, in this case, division. So our first term is 8.75. So our zero term would be what? We have to take 8.75 and divide it. So our zero term should be, if we are looking at it, 4.375. And again, if you don't have your calculator out, grab your calculator out, grab one in the front of the room as we are looking at these, because it will be helpful as you're doing this next page as we are looking at some of the ones here. Okay. Any questions on this as we're looking? All right. So the next one is talking about you have $2,000, you're invested at 6% compounded annually. So when we are thinking about our common ratio, it says, is there a way to express this situation as a geometric sequence? Yes, we can do this. We need to find and figure out the constant ratio that we need to figure out in terms of 2,000 is our zero term, first, second, and write an explicit formula. So the first thing that we want to keep in mind with this is our common ratio. So they said a 6% compounding, keeping in mind that when you do that, you are looking at 1, which is 100%, right? 100% is equal to 1, plus our 6%. And 6% as a decimal is 0.06. So when we are looking at our common ratio that we are looking at, our constant ratio for this one is going to be 1.06. So when you are taking a look, we want to put, so as you look at it, we are looking at our constant ratio being 1.06. So now we are looking at, in terms of our values, and this is where sometimes it gets a little confusing, 2,000 is our initial, that's our term 0. And after 1 year, you're going to have $2,120. So a lot of times people think that the 2,000 is the term 1. So you just got to be really careful for this as you are looking at it. The term 1 is going to be after you've multiplied. So when you're thinking about this, how we got this value is we took 2,000 times 1.06. That's what we're looking at. And as we look at this last part, our sequence then as we are writing it, this is going to be because it's the 0 value. So it's 2,000. So it almost looks exactly like our exponential equations. G to the n equals my 0 term, 1.06. This would be n minus 0. N minus 0 is simply going to be n. My first term, if I'm writing it as an explicit formula, is going to be 2,120, 1.06 to the n minus 1. I don't care which one you use. Both are going to work. I will take both answers as we are looking at this. Okay? So now we want to take a look at that next one down. So it talks about you're selling a car sold for $22,000. Suppose it has a decrease of 12% a year. Meaning we want to take our 100% and add or subtract 12. Subtract 12%. So 100 minus 12 is going to give us 88. 88% is a decimal, 0.88. So be really careful for that when you're looking at it. So we want to write a formula to find the value of our car. So a lot of times the easiest one is, this is our starting point, the 22,000. So G to the n is going to be equal to 22,000 times 0.88 to the n. Our 0 term, 0.88. So now we are going to just be filling in. Instead of G to the n, we're going to write G to the 5. So G to the 5, if we are writing that down, G to the 5 is going to be equal to, the reason they use G is because it's geometric. The reason we use A is for arithmetic. 0.88 to the 5. So take your calculator. Cent on this one. Sierra, what'd you end up with?
11,610.10 cents.
Thank you. Because we are looking at that. So now we are looking at this next one. I'm going to have you kind of work with your shoulder partner as you are looking at it. Recursive, remember you want to start with G to the 1, and then you're going to have G to the n. And I do need to have for n greater than 1, as we are looking at this one. And when you start your explicit, it's going to be G to the n. So first thing you want to take a look at is what is our common ratio. So if I'm looking for the common ratio, what would you say our R value is going to be as you're looking at this? You go with 1/2. Okay. So I would like you to try and write your recursive formula and your explicit. Talk to your shoulder partner, and I'm going to call on you in just a minute. Partners on both of them. Aletta, what do we know our G to the 1 is? 8. G to the 1 is 8. And then if we are looking at it, Jared, what did you have for the rest of yours? Did you guys have that for this part? So 1/2 G to the n minus 1. A lot of times they're going to put this in a parenthesis. Do you have to? No. Sometimes you might notice that they put the half in a parenthesis just to kind of separate it so that you can see the terms for n greater than 1. Okay? If we are looking at our explicit formula, as we look at our explicit formula, Casey, what did you start with? G to the... Mm-hmm. That look right?
Yeah.
Keep going. To the times. So making sure, remember, this is our first term, this is our second. You could have used any of these. So I could have seen G to the n is equal to 2 times 1/2. But if I use 2, then I have to use n minus 3, right? Because it's my third term. So I don't care which one you use. Most people generally like to use the first one. This one is using the 0 term, right? So what would be the term before 8 would have been 16. That's my 0. That's how they had this one, okay? So it doesn't matter which one, but you just got to be really careful. And the question I always get is, well, how do I know if I did the right one? Well, plug in the numbers, right? So if you want to check, this is the 4th term. So if I wanted to find G to the 4th, and I go to this equation, and I put in my calculator, 8 times 1/2 to the 4th, I should definitely get, if I am looking at this, 1, if I am looking at that. G times, not 4, it should be what up here? 3, because I was taking 4 minus 1. 8 times 1/2 to the 3rd, well, 1/2 to the 3rd is 1/8, and if I take that times 8, it does give me 1, which is that term. If I plug in 4 here, 16 times 1/2 to the 4th, I should get 1. So I can always check these, so making sure you understand how you can check them. So as we look at this kind of last page of your notes for this unit, as we are looking at this, so it says a ball is dropped from 50 feet, and it bounces at 90% of its previous height each bounce. So let h of n be the height after n bounces. So we want to start with our explicit formula. As we look at our explicit formula, the first thing I want you to talk about with your shoulder partners is I just want you to identify what is, if we are taking a look at this, is 50 the 0 or the first, after the first bounce, and what should I use for my multiplication factor? Should I use 90%? Have we had a bounce? We have not had a bounce. So our h to the 0 is 50. H to the 1 is after the first bounce. Should I be using for my common ratio 0.9, or should I use for the common ratio 0.1? So how high up is it bouncing back? Only 10% or up 90%? It's going up 90%. So a lot of times we've been subtracting. This one we actually are using because it bounces to 90%. So if it said it bounced less than 10%, you would have taken 100 minus that. So when we are taking a look at our explicit formula, this is what I'm going to be kind of looking at. H to the n, 50, times my 0.9. You can use 0.9 instead of 0.90 to the n. Why to the n? Because it's n minus 0, right? So if you want to actually write n minus 0, you could, but n minus 0 simply is an n. So now we're looking at our recursive formula. So put in your calculator. We need to find the first term, right? So you got to replace this with a 1, and our h to the 1, as we are looking at that, is going to be how much? H to the 1 comes out to be 45. So if we are taking a look at that, we're going to start with 45, h to the 1, after 1 bounce. Now we want to write our recursive formula. H to the n is going to be equal to, what are we multiplying by? 0.9. H to the n minus 1 when n is greater than 1. You are now asked, as you look at it, to find g to the 10. So you kind of think of this picture down here. So if we look at it, it started up here, and then it's here, and now it's here, and the ball's bouncing. So after 10 of them, if it keeps going, we are going to find g to the 10 is equal to, Jethro, how would I start it out? Which formula do you want to use? The recursive or explicit? Recursive. So recursive, I'm going to have to find g to the 2, g to the 3, or h to the 3, 4, 5, 6, 7, 8. So instead I should use explicit. So h to the 10, not g, I'm used to writing geometric, equals, so we're going to go 50 times what, Jethro? 0.9?
Yeah, 0.9, and then to the 10.
And I'm going to go to the 10 power. So use your calculators, please, put that in. H to the 10, if we are looking at it, how many feet? So it started way up at 50 feet. That's pretty high up, right? If we think about 50 feet up, right? And it's now bouncing. And then, Lindsay, what'd you guys get?
17.4 feet.
17.4 feet. So you're going to want to label your answer, h to the 10 equals 17.4. When you take the test, yes, you'd want to show me what you did to get this answer, because sometimes some of you will just put it in your calculator wrong. So if you mess it up on that part, at least I can see how you put it in and what your answer was as you were looking at. So today you are looking at your homework